You've conducted a literature review, and now you have a research question. Let's take a look at the data.
Raw data consists of long lists of numbers and labels that don't seem to be very informative. Raw data lacks context. Exploratory data analysis is what you use to make sense of the data. You do this by converting data from its raw form to a form that makes sense, that has context, that tells the story you want to tell. Basically, exploratory data analysis consists of organizing and summarizing raw data, looking for important features and patterns in the data, looking for any striking deviations from those patterns, and interpreting your findings in the context of the problem or research question. We begin exploratory data analysis by looking at one variable at a time, also called univariate analysis. In order to convert raw data into useful information, we need to summarize and then examine the distribution of any variables of interest. By distribution of a variable, we mean what values the variable takes and how often the variable takes those values.
If we were studying a small number of observations, we could do this with a pencil and paper, a calculator, or even in our heads. The data sets you're working with often have thousands of observations. Working with such large samples is only achievable if we use statistical software. These software programs require the use of syntax or formal code to retrieve, analyze, and manipulate data. Learning to write code, learning the proper use of syntax, can really expand your capacity for engaging in statistical applications and is a central skill you'll learn in this course. This skill will also greatly expand your capacity for engaging in deeper levels of quantitative reasoning about data.
For this course, you'll be using R and RStudio. R is a very powerful statistical package. Looking at all the windows, menus, and features, though, can be rather daunting, so it's important for you to realize that this course will introduce you to the basics of the software and the syntax. You'll learn what you need to know to get started asking and answering interesting questions about data.
Have you had that consistently?
In the beginning, it may feel like you're learning another language. Basically, you are. As you work through your project, you should begin to feel more comfortable implementing the various decisions you'll be making about the data. When you need help, seek it from your course moderator, professor, your peers, or from course discussions.
Now you need to install R and RStudio. Follow the available instructions in the document called Getting Started with R. Now that you've installed R in RStudio, it's time to start learning to write a program. Open RStudio if you haven't already. When you open RStudio, you're also opening R. RStudio provides tools that make it easier to work with R and its libraries. The following videos are full of important information. They introduce you to writing code in R. Please work at a comfortable pace and stop the video to work on your program and incorporate what you're learning as you go along. Here's how to begin. The first time you open the program, the console, where you execute commands, will take up the left side of the screen, and the file window on the lower right will show the default directory. You want to set your working directory to the folder which contains your data and where you want to save and write files. To set the working directory, go up to Session on the menu bar at the top of the screen, select Set Working Directory, and then choose Directory. From here, you can browse to the folder where you want to save your work for this class. As an example, this working directory is set to a folder within Documents called R. Once you've found the folder where you want to save your work for this class, click Select Folder, which sets that folder as the working directory. This allows you to save all of your R files and to import and run data sets from this directly. So let's write a program. Select File, New File, and R Script. This will open a new window on the top left above the console. In RStudio, this window works similarly to a word processor. It automatically uses color coding to help you write and debug your program. Blue font indicates an R keyword. Numbers are shown in a darker blue. Green is used for text strings. A string in R consists of alphanumeric or other characters enclosed by double quotation marks. A light green is used to show comments, which starts with a number or pound sign. R is case sensitive, so be sure to use the correct capitalization when you write your programs. There are a few basic steps that R and all other statistical software languages require when you begin writing a program. If you look at the console window, you'll see that selecting a working directory provided you with a corresponding command that starts with setwd. So that you do not need to set the working directory each time you open R, it's important to copy this line of code and paste it as the first line of code in your program. Next, you'll load the data set that you'll be working with, which is in the form of an R data file and has the extension .rdata. This step is also sometimes called reading or calling in the data set. To be able to load data, you'll first need to download the .rdata file from the course site into the directory where you're keeping your class files and where you've set your working directory. Once the rdata file is downloaded into your working directory, the code for loading the NESARC data is load parens quotation mark NESARC_PDS.RData quotation marks in parens. We use the function load to access the data set. In R, functions are always followed by a set of parentheses. Remember that. As shown here, you include the name of the data file you want to load inside either single or double quotation marks and parentheses. Alternately, if the data set is located in a different folder on your computer or on a network drive, you would need to include the full path name in your code. Here's an example. If you chose the Mars crater data set, the word NESARC_PDS would become Mars crater_PDS. For the National Longitudinal Study of Adolescent Health, the name would be changed to AdHealth_PDS. If you chose the Gapminder dataset, the name will become Gapminder, and so on. The name of the dataset that we've selected for our sample research is NESARC_PDS. To run your program, put your cursor on a line of code in your R program, then click the Run icon, which is located to the left of the program window. This will run the current line. After you load the dataset, you should see the name of the dataset in the Environment window on the top right of your screen. This window lists all the objects that are currently available in your R environment or your R session. Right now, the only object is the NESARC dataset, often called a data frame in R. You can also see its dimensions, 43,093 observations or rows, and 3,008 variables or columns. Click on the NESARC object in the Environment window, and part of the dataset will appear as a tab in our Script or Program Editor window. R will also print the function View Parens to the console, which was used to display the NESARC dataset. You can see that the columns represent the variables in the dataset, and the rows represent the individual observations or participants in the NESARC survey. It's important to have a variable in your dataset that uniquely identifies each observation, often called the unique identifier. In the NESARC dataset, it's called ID_num. You can see this variable in this first variable column. You want to make a copy of the dataset to work with and to give your copy its own name. Here, going back to the program file, we're going to add code that copies the NESARC data and calls this new dataset data. However, you can call it MyNESARC or MyData or any other name of your choosing. This name is what you will use to refer to the dataset when you're working with it in R. Data, assignment operator, NESARC. Use the assignment operator, which is a less than sign followed by a hyphen, to tell R to make a copy of your data set and store it as the new data frame or object. The assignment operator looks like an arrow, which can help you remember that the value or expression on the right-hand side gets stored in the new object that's named on the left-hand side. Put another way, R takes what's on the right side of the arrow, evaluates it, and stores it in the object on the left side of the arrow. Be sure to use the name on the right-hand side of the assignment operator that appears in your environment window, which is not necessarily the same as the name of the R data file. When you select and run this line of code, the new object, data, pops up in the environment window. You'll be able to create many objects in R, but it's important to remember that R is case sensitive, so the object data in lowercase letters will be stored differently from data in uppercase letters. All of the code that we'll write after this statement will work with this data set we've named data. Before we move on, let's save this program. To do this, click the Save icon on the top left of your program window. The default name is Untitled, but you should feel free to rename the program as you like. Here, we name it NESARC Program. The R program, also known as an R script, will be saved to your working directory. This file with the extension .r is essentially a specialized file containing all of your R code.
Remember, we stated exploratory data analysis begins by looking at one variable at a time. This is called univariate or descriptive analysis. In order to convert raw data into useful information, we need to summarize and examine the distribution of any variables of interest. The variables of interest are the variables of interest to you, the researcher, in answering your research questions, addressing your research problem, and telling the story you wish to tell with your research. By distribution of a variable, we mean what values the variable takes and how often the variable takes those values. Here's an example.
A random sample of 1,200 U.S. college students were asked the following questions as part of a larger survey. What's your perception of your own body? Do you feel that you're overweight, just about right, or underweight? This table shows part of the data, 5 of the 1,200 observations. Information that would be interesting to get from this data includes what percentage of the sample students fall into each category. Or, how are students divided across the 3 body type image categories? Are they equally divided? If not, do the percentages follow some kind of pattern? There's no way that we can answer these questions by looking at the raw data, which are in the form of a long list of 1,200 responses. That's just not very useful. However, all these questions will be easily answered once we summarize and look at the frequency distribution of the variable body image. That is, once we summarize how often each of the categories occurs. In order to summarize the distribution of a categorical variable, we first create a table of the different values or categories the variable takes. How many times each variable occurs, which is the count, and more importantly, how often each variable occurs, which is expressed by converting the counts to percentages. Now that we've summarized the distribution of the body image variable, let's go back and interpret the results in the context of the questions that we posed. What percentage of the sample students fall into each category? How are students divided across the 3 body image categories, and are they equally divided? You can see that most of the samples, that is 71.3%, felt that their weight was about right, and that a comparatively small percentage felt underweight at 9.2%. The overweight category was 19.6%. Go back to your R program now to learn how to use the frequency function to generate distributions for the variables of interest that pertain to your research question. The frequency function is in the library DESCR, and you'll need to load that library each time you start RStudio. Libraries or packages are collections of R functions that others have written to add on to the basic functionality that's built into R. Each time you run your code, you'll need to tell R that you want to use functions from a specific package. To do this, use the syntax library, parens, package name, close parens. If you followed all the instructions on the document Getting Started with R, then you should already have installed the packages you'll be needing for this course: Descriptive Statistics, the DSCR package, and Herald Miscellaneous, the HMISC package. To install a package, go to Tools in the menu toolbar, Install Packages, and then start typing in the name of the package you want to install. It will start to auto-complete the package names. Choose which one you want and click Install. You only have to do the install step once on each computer you use. But you need to run the library function in your program each time you reopen R and want to use a function from that library. Now that we've installed the DESCR package, we can use it by typing library, parens, DESCR, close parens, and selecting Run. To generate frequency distributions with the DESCR library, we use the frequency function freq. Like all functions, freq, followed by parens, needs an input inside the parentheses, which is the variable you're interested in looking at. Since each variable only exists as part of your dataset or data frame, you need to tell R where to find that variable by typing the name of the dataset, followed by a $sign before the variable name. Freq, parens, data, $sign, variable name, close parens. Before we actually run any frequencies, we should add labels to our variables. Because the actual variable names are cryptic, it's a good idea to give them labels that are easily interpreted at a glance. We'll return to our program and show you how to generate variable labels for your output. We do this using the command label. However, since this function is in the library HMISC, that library has to be loaded first. Click on Tools, Install Packages, type HMISC, and then click Install. Once you've installed this library, you can add this library package to the program to be run. Then you can highlight both library commands and run them now. The label function takes as an input the name of the variable you wish to label, accessed through the dataset using the $sign. A clear description of the variable in quotation marks is assigned to the label function using the assignment arrow. Note that each label statement should take up only one line of code and not have any breaks. Library, parens, HMISC, in paren, label, paren, data, $sign, tab 12 MDX, assignment arrow, quotation mark, tobacco dependence past 12 months, in quotation.
For my research question, I'm interested in looking at the association between how much a person smokes, that is, quantity and frequency of smoking, and the presence or absence of nicotine dependence. Going back to the NESARC codebook, you may recall that I have a number of variables that measure smoking behavior and nicotine dependence. It's the actual name of the variable, rather than the longer descriptive name, that I'll include in my program in order to generate frequency distributions. I have the names of each of the variables circled here in red.
You'll write one line of code for each variable that you want to examine. Type freq, and then inside the parentheses, the name of the dataset, followed by the $sign and the name of the variable. Here's our example R program thus far with the frequency functions added. You have your load command, you have your data command, your library commands, you have your label commands, and your frequency commands. When you add label and frequency functions for your variables of interest from the dataset you've chosen, you've completed your first R program. You'll build on this program as you progress through your project. Before you run the program, you should go to the Files window in the lower right portion of your screen. You can increase the size of this window by clicking and dragging the top edge of the window. This will give that portion of the window room to display graphs generated by the frequency procedure. Then you just need to click the Save button at the top of the program or script window. You run the program by putting your cursor on a line of code in your program and then selecting Run. Once your program has finished running the commands, the output and any error messages will appear in the console window. In this example, the program has run successfully. We can tell it's run successfully because as we scroll through the console, commands, shown in blue, will be followed by the appropriate output, which is frequency distribution in this case. If the program ran successfully, there will be no error messages in the console window. Error messages are typically indicated in red font. If you do find any errors listed, go back to your script, correct the errors, save the corrected code, and then run the program again. In addition to the frequency table for nicotine dependence in the past 12 months that we see in our console, this command generated a bar graph, which visualizes the frequency of responses across all levels of this variable. You can see that there are more than 38,000 individuals without nicotine dependence and nearly 5,000 with nicotine dependence. You can also run multiple lines by highlighting multiple lines before selecting Run. Here, you can scroll through the results to examine the frequency distribution for each variable. You can also click the back arrow in the plotting window to examine each of the graphs displaying the frequency distributions. Now you can see that the frequency distributions include both the variable name and the variable labels. Let's look at the first table, which shows the distribution of responses for the variable tobacco dependence in the past 12 months. The NISARC codebook tells us that 1 means yes and 0 means no. Following this list of response values, the table also shows the frequency of each and the percent of individuals with and without nicotine dependence. For variables that include missing data, a column showing percent of valid data will also be displayed. By consulting the codebook, you can interpret and describe each of these frequency tables in the same way. For some variables, you'll want to get the cumulative percent. You can add another column to the frequency table by adding the as.ordered function. Let's do this for the smoking frequency and smoking quantity variables. Freq parens as.ordered parens data $, S3A Q3B1 close parens. Mimic that for the next variable. Save, and then highlight and run these two lines of code. After running these lines of code, we see an additional column, cum%, standing for cumulative percentage. This can allow you to evaluate your data more fully. For example, looking at the cumulative percent column for smoking quantity, we can see that about 15% of adults in the NISARC dataset smoke 3 or fewer cigarettes per day. Once you've examined frequency tables for your variables, the next decision you need to make is whether you want to subset the data and ask a question based on specific observations, or whether you want to ask the question of the entire sample. In other words, are there particular rows in the data set, that is, individual observations, that you want to keep and others that you want to exclude? For example, we're most interested in the association between smoking and nicotine dependence in young adults who may still be establishing their smoking patterns. Therefore, we decide to examine only those adults who are 25 or younger and exclude all adults older than the age of 25. We also decide that we want to focus on recent smokers rather than individuals who've smoked more than a year ago. So the original research question for our example is further clarified to include the association between smoking and nicotine dependence, but only among young adults who have smoked in the past 12 months. The research question is not changed. Rather, the question will be asked based only on a subset of the observations that are available in a specific data set that will help answer the research question. To implement these decisions, we'll go back to our program and add an additional statement immediately following the statements that load and copy our data set. Specifically, we'll add a logic statement that tells R to include only those observations that will help us answer our research question. A logic statement requires one or more operations. Here's a table of common operations used in R. These include equal to, not equal to, greater than, less than, greater than or equal to, and less than or equal to. The following logic statements will need to be added to this program in order to call in the specified subset of the observations now to be used as the basis of the research question. Sub 1, assignment arrow, data, square bracket, data, $, check 321, equal 1, ampersand, data, $, age, less than or equal to 25, comma, close square bracket. This line of code creates a new data set that we're going to call sub 1, and it will contain only those rows, that is observations, that satisfy both logic statements. Our logic statement indicates that check 321 equals 1. In R, equals is displayed with a double equal sign, and that age is less than or equal to 25 years old. Square brackets are used to specify certain rows or columns in a data set. We need to tell R whether we want to specify rows or columns. The format for this is dataset name, square bracket, which rows observations, comma, which columns variables, close bracket. Since we want to specify certain rows, the logic statements for check 321 and age, joined with an ampersand, go inside the open square bracket and before the comma. Now let's run this. Here you can see this new sub1 object has popped up in the environment window. Sub1 is the NESARC data set that includes only young adult smokers who've smoked in the past 12 months. If we click on the sub1 object, we get a tab in our script editor window that displays the new data set. However, many of the observations have an NA, which is R's representation for missing data. This is caused by missing data in either the age or check 321 variable. We need to command R to exclude these missing observations. Otherwise, R will put these missing values into the data set also. To do this, we modify the command by adding logic statements that remove missing data for the age and check 321 variables. What we're going to do is modify the sub1 command. Here, the code asks for observations in which age is not equal to NA, and here the code asks for observations in which check 321 is not equal to NA. Putting an exclamation point in front of an is.NA asks for observations in which values for that variable is not equal to missing, or in our language, is not equal to NA. The is.NA function basically evaluates whether or not a value is an NA. The format for the remainder of the code remains unmodified, and it follows the model dataset name, square bracket, which rows, comma, which columns, in square bracket. This is where we define what observations or rows we want to keep on the left side of the comma, and what variables or columns we want to keep on the right side of the comma. We still want to include all the columns or variables, so we can leave a space after the comma and before the closing bracket. Even if you want to keep all the rows or all the columns from a data set, you'll still need the comma so that R knows whether what you specified refers to rows or columns. Now save and run this line of code that creates the sub1 data set. Now, let's rerun our frequency distributions, but this time based on the observations in our new sub1 dataset. Freq, parens, as, dot ordered, parens, sub1, $, tab 12 MDX, close paren, and you follow that model. Let's also add the code to our program to get a frequency table for the variable age drawn from our new sub1 data set. Now, when these lines of code are saved and run, you can see frequency distributions for each of the variables, but only for the 1,706 individuals aged 18 to 25 who reported smoking in the past 12 months.
I can be confident that I am now working with this sample because, as you can see, all of the 1,706 observation has a 1, meaning yes for having smoked in the past 12 months. And if I scroll down to the distribution of age, I can see that only 18 to 25-year-olds are included in the sample. If for your own research question you are completely unsure at this point whether or not you want to limit your question to a subset of observations, no worries. In that case, there would be no need for you to add any additional logic statements to your program. This is always a decision and an example that you can revisit in the future.
Throughout your program, you should also include notes preceded by the number or pound symbol to help remember what specific lines of code do. As you keep adding to your code, it will become difficult to remember why you wrote what you wrote. Here's a note added to our example code. It's a note to remind ourselves that the data is being subset to include only past 12-month smokers aged 18 to 25. The note is written in light green within the program. By using the pound or number sign, you're able to comment out your notes so that R does not read them as actual programming statements. You should definitely use this commenting out technique early and often as you build your program. These notes can be very important because they'll help you keep track of decisions you've made and actions you've taken in writing your code. Once you're satisfied that your R script is correct and complete, you can make use of R Markdown in order to produce a notebook or report file that integrates your R commands with their corresponding output. You can do that by clicking on the notebook icon at the top of your script editor window near the middle of that window. Clicking on this icon opens up a box that says Compile Notebook from R Script and asks you to select the format of the notebook. The default is HTML. We'll select that and click Compile. An HTML file should automatically open once the program is complete. You can save that to your computer as a report. Please be aware that all syntax errors must be corrected before compiling a notebook with R Markdown. The report file will not be created if there are any errors in your R script. At this point, and whenever you've added something to your code, you should save it. It's highly recommended to keep one detailed, commented, and organized R program for your project. This is because you'll want to have a program file that you can use to rerun the commands you've written. When you close RStudio, it will ask you if you want to save your workspace. Saving a complete, accurate, and well-organized R script file makes it unnecessary to save the workspace image, so you can select No here. You now have the tools you need to complete assignment 2. For this assignment, you should write R code that displays frequency tables for the variables that you've selected for your research question.